Welcome Alexander Levin from Catholic University of America, and he will speak on the generalized Gröbner basis and dimension polynomials over finitely generated non-commutative algebras.
Thank you. Thank you for the invitation. So I'll be talking about quite a wide class of algebras over which finitely generated modules can be characterized by dimension polynomials. So we'll start with a field with a set of derivations and set of injective endomorphisms that compute with each other. So the derivations are skew derivations corresponding to the endomorphisms. So we have this relationship that you have seen several times already. Now, let theta denote the free commutative semigroup generated by the set of, by the set of indeterminates x1, xn, and we consider the ring of Ore polynomials generated by those variables. So the set of these Ore polynomials is a ring, so it consists of such finite sums, and it's a ring with respect to this multiplication. So it's a regular Ore polynomial, a ring of Ore polynomials. Now we fix a partition of the set of variables, this one, in P subsets, and elements of theta will be called monomials. The order of such a monomial is with respect to each set of the partition is defined as the sum of exponents corresponding to this set, and we can also introduce the total order of theta as the sum of such orders. Also, we consider p different orderings of the set of monomials. Orderings are defined according to the corresponding set of the partition. First, you consider order with respect to this subset, and then total order, etc. So, in this way, we get p total orderings of the set of all monomials. Then, if you have non-negative integers r1, rp, then we can restrict the orders of monomials with respect to each subset, and get this set theta of r1, rp as a subset of the total set of the set of all monomials. And then dr1, rp denotes the subset of d generated by monomials of orders at most ri with respect to each subset. In this case, we get p-dimensional filtration of the ring D. And also we will introduce the following notation. If f is an element of D, then theta of f will denote the set of all monomials that appear in f with non-zero coefficients. And we can naturally extend our orders to quasi-orders on D. So this is so f is less than g with respect to the corresponding order if there is a term in G but not in F, such that higher terms appear in F if and only if they appear in G. So it may, in particular, if the highest monomial in G is higher than highest monomial in F, then G is higher than F. If they are equal, then you compare next monomials, etc. So far this is just a well-known ring of Ore polynomials. Now we introduce new binary operation. And with this operation, instead of old multiplication, we obtain so-called skew-solvable polynomial ring. The term comes from the work by Kendry-Roddy and Weiss-Fenning. They did this construction on a ring of commutative polynomials. So this new binary operation should satisfy the following axioms. So first of all, the ring should be associative. Then, in most cases, it is the same as old multiplication. But when you start commuting variables, then we have this kind of multiplication. So xi and xj do not commute. They commute up to polynomial lower than xi, xj. Now, this construction in particular includes the following important examples. First of all, of course, rings of order polynomials, difference differential operators, rings of those operators, while algebras, then quantized while algebras in case of, say, trivial or some other partitions of the set of generators. So this is just a description of quantized while algebra, which is generated by 2n variables with this defining relations. So the lambdas and q's are constants of the basic field, actually invertible constants of the basic field. Now, we leave aside the problem when this is associative ring. So, because this is the hard problem, it's not solved. When axioms 2 to 4 imply that this is associative ring, but in the examples we always have this condition. So all those rings are associative rings. Now some terminology here. If you have two monomials, we say that one of them theta divides theta prime if just the k's are less than else, and consider this as a quotient. Now, of course, it's not quotient in regular sense. When you divide, you get some relation of this kind. So it's up to a polynomial of lower polynomial, and we require that this polynomial is lower with respect to any of these orders. We can introduce the concept of least common multiple in a similar way. And when you multiply two monomials, then you have this relationship. So we have some coefficient in k that depends on theta 1, theta 2, and g is smaller than this monomial with respect to any of those orders. Now, we also, as above, we consider the filter ring. Oh, sorry. There's something here. Yeah. And then we can consider a module. By the module, we always mean left module of the ring. And for such a module, we can consider a family of vector k subspaces of M. And this family is called a p-dimensional filtration of M. If we have the following property, so this is ascending chain of vector subspaces with respect to each index here. The union is whole module M, and you have this natural inclusion as we have for any filtration. Now, if in addition every vector space is finitely generated and we have eventually we have equality, then we say that filtration is excellent. As an example, we can take finitely generated module and consider this natural filtration, which is excellent. The filtration generated by the filtration of the ring D. So now we are going to introduce the reduction in a free module over the ring D. So consider a free module E with free generators E1 AM over D. Then elements of the form theta EK are called terms. The set of terms are denoted by theta E. By the order of a term, we mean the order of the corresponding monomial theta, and the same order with respect to group Xi, I mean subset Xi of the set of unknowns. And we say that term is a multiple of another term if simply theta is a multiple of theta prime and I equals j. So in this case we use the same notation as when we divide monomials. We can also divide the least common multiple of such two terms as least common multiple of theta 1 and theta 2, provided that I equals j. If not, then least common multiple is 0. And we can extend the orderings of theta to the P orderings of the set of terms theta E, defined as follows. So if we have two terms, then we first compare thetas, and then we compare the indices of E's. And also, when you have to term from monomial from theta and term, then bar denotes the leading term of this product. So when you multiply, you have some remainder of lower order. Now, if obviously theta E form a basis of K vector space E, and every element can be uniquely written in this form with different A's, and then we can naturally consider leader of this element with respect to each of P orderings. So this element, such elements are called element maximum with respect to order J is called the J leader of the element F, it's denoted by this symbol UFJ. Of course, it's possible that two different leaders are equal to each other. And the order of this leader is called the Jth order of F, and it is denoted by this symbol. And the corresponding coefficient is denoted by LCJ of F. Now, the concept of reduction is introduced. First of all, we say that if you single out several orders of this kind, we say that F is order K, I1, IR reduced with respect to G if F does not contain such a multiple of the kth leader of G such that orders when you multiply by the same theta of other leaders of G do not exceed the corresponding orders of leaders of F. So we need this definition, so when you perform the reduction and you eliminate the highest term with respect to kth order, you don't increase the orders with respect to other orders. So when you consider a reduction, you simultaneously look at what happens with the other orders. And we say that F element is reduced with respect to a set if it is reduced with respect to every element of this set. Now we are going to introduce the concept of Gröbner basis with respect to several orderings. So we introduce P-1 new symbols. This is formal definition of the Gröbner basis. Consider the set of monomials of this kind, and consider the semigroup of the terms with whose coefficients are monomials of this kind, so these terms. And then we consider this non-negative integers. So this is order with respect to I of the leader with respect to I, and order with respect to I of the leader of the first leader. So of course this is non-negative integer because that's how we define orders with respect to I. And then we consider natural mapping from E to this semigroup such that we have leader with respect to the first order multiplied by this monomial. And the definition of if you have if n is a D submodule of E, then a finite set G is said to be a Gröbner basis of n with respect to orders 1 up to P if for any f in n there exists element of G such that row of Gi such that row of Gi divides row of f. So as elements of the semigroup. Now, the definition implies that any such Gröbner basis is at the same time Gröbner basis with respect to first order. And therefore, in the usual sense, with respect to order 1, and that's why it generates the module. And if we have just set of elements of E, then we say that this is a Gröbner basis. If this is a Gröbner basis of the submodule generated by these elements. Now, we say that if you have three elements, f, g, h, g is not 0, we say that one of them reduces to, that f reduces to h modulo g in one step. If you have, if and only if there is some term w such in f such that ugk, this leader with respect to k, divides w, and we have this relationship. So it's like it is designed to eliminate the highest term with respect to order k. And at the same time, it should not increase the orders with respect to the orders of monomials with respect to other orders. Okay, so here we just define, in the same way as we define multiplication in theta, we can consider multiplication of theta by a term. When you multiply, you get this element c that appears when you multiply monomials. Now, as usual, we said that element is reduced with respect to f reduces to h according to the sequence of orders k, I1, IL modulo g. If there is a sequence of elements of g such that you have sequence of reductions in one step. Now we have these two statements that are similar to classical statements about Gröbner basis. So if you have Gröbner basis with respect to these orders, then there are elements g, so you can find element g which is reduced with respect to this Gröbner basis, and which is comparable such that f minus g is a linear combination of the elements of the Gröbner basis. And the second proposition says that if g is a Gröbner basis of d sub module n of E with respect to this sequence of orders, then f is in n if and only if it can be reduced to 0. It reduces to 0 actually. And if f is in n and it is reduced with respect to the Gröbner basis, then it is 0. Now we can also consider S polynomials with respect to the order k, and that's how they are defined. So we consider corresponding least common multiple, and so this is S polynomial with respect, it's called kth S polynomial. So we consider analog of S polynomial considering order k. And the main proposition here is as follows. That actually gives algorithm how to compute such a Gröbner basis. So if you have Gröbner basis of a d sub module n of E with respect to each of the following sequences of orders. So here order with respect to p, then for Gröbner basis with respect to two orders, etc. Then if kth polynomial, so polynomial with respect to order k, all those S polynomials reduce to 0 modulo g, then this is a Gröbner basis with respect to this sequence of orders. So you add one order to the sequence. And therefore, using this proposition, you can find a Gröbner basis with respect to sequence of orders 1 up to p, starting with just regular Gröbner basis with respect to this order, then getting Gröbner basis with respect to two orders, etc. The first step is just regular Buchberger algorithm, and then you have this generalized algorithm using S polynomials with respect to k, in this case p minus k. So now this type of Gröbner basis can be used for computing and proving the existence of dimensional polynomials. The main proposition in this direction is the following. So if you have d module generated by a finite set, and the corresponding free d module generated by free generators u1m, the same number m, you have natural epimorphism from E to n. Take it kernel, take Gröbner basis of this kernel with respect to this sequence of orders. And then if you have module, if module has this filtration, this is natural p-dimensional filtration of M, you can consider two sets. One set of terms which are not multiple of any leaders, one leaders of G. And the second set of terms that are multiples of leaders of G, but multiples that increase some of the other leaders. So they don't hold the orders with respect to other orders. And then U is the union of these two sets. Then this image of this set U is the basis of MR1RP, so element of this filtration over K. So then it remains just to evaluate the size of this set and the size of this set. So as I said in a previous talk, these problems were solved in about 15 years ago when we considered polynomials, dimensional polynomials of subsets of n to the m of subsets of n tuples. So therefore we have the following theorem about dimensional polynomial of module equipped with p-dimensional filtration over rings over this skew solvable polynomial rings. So with this condition, if you have excellent filtration, in particular filtration corresponding to generators, there is a polynomial in p variables with the rational coefficients that describes the components of this filtration. Degree of polynomial with respect to each variable does not exceed the cardinality of the corresponding subset of the partition. It can be written in this canonical form with integer coefficients. And it has many invariants. If for any permutation of the set 1 over p you consider the corresponding lexicographic order, and for any subset of n to the p, for any subset sigma pi denotes the set of all elements maximum that are maximal in this set with respect to one of these orders. Then we have a bunch of invariants of this polynomial, so its degree, coefficient n1 and p, elements of this set of all p tuples where coefficients are not zero, then total degree and all coefficients of total degree d, where d is the total degree of the polynomial. All those numbers are invariant, so they don't depend on the choice of the generators of this module M. And as a consequence, we can apply this to Weil algebras that are algebras also of this type we are considering. So I remind you that Weil algebra is generated by two n variables with this relationship. So all variables commute except for di and xi. They commute in this way. And every element has a unique representation of this form as a sum of monomials of this kind. We can introduce the order of such an element as just sum of exponents, and also orders with respect to variables x and partial derivations. Then we have, from one hand, when you consider just total order, you have natural filtration of any module over Weil algebra. So you have, first of all, you can consider filtration of Weil algebra itself, just restricting the order of the elements. And also, if you have module over such algebra, you can consider the natural filtration if module is finitely generated. Then you consider filtration of this module. Now, the following result is the classical result of Bernstein, who introduced this kind of polynomials and solved open problems stated by Gelfand in mid-50s. So, with this condition, there exists a polynomial with with rational coefficients that describes the dimension of components of filtration. Degree of this polynomial is between n and 2n. And if it is written in it can be written in this form, where where this d factorial times ad is an integer, and this integer does not depend on the choice of set of generators of m, so those are invariants. The degree and this integer d factorial ad is the leading coefficient of Bernstein polynomial. And they are called Bernstein dimension and multiplicity of the polynomial. Now, if you consider bifiltration of A and K according to the degrees with respect to x in partial derivations, and the corresponding bifiltration of a finitely generated module over nk, then our main theorem implies that we have polynomial in two variables, such that for sufficiently large R and S, this polynomial describes the dimension of the components of this bifiltration. Polynomial can be written in this form, and it has invariance corresponding to the invariance described in our main theorem. So we have two orderings, two lexicographic orderings on N2. Then these numbers are invariant, so they do not depend on the system of generators of the model, its degree. Those coefficients, where mu1, mu2 are maximum elements of this set of ij. Aij is not 0. Those are maximum elements with respect to one of these two lexicographic orders. So those numbers do not depend on the system of generators. So we have many more invariants than we get from Bernstein polynomial. And I'll complete with example, just a small example, when you have modular one-while algebra with this defined equation. And so it's simply a factor module of free module by this submodule, which is this element. And then if you compute by a polynomial in two variables, that's what we get. A and B are those exponents. While classical Bernstein polynomial is this one. So if you compare these two theorems, Bernstein theorem says that there are two invariants, the degree of this polynomial, which is 1, and coefficient A plus B. Our theorem gives us 3 invariants, degree 1, A plus B, and A, those coefficients. And therefore, this polynomial in two variables determines both parameters of the equation, while Bernstein polynomial, as you see, determines only the sum of the parameters A plus B. So it can be also applied in other settings, but I'll just give one example. So thank you.
Questions? Comments?
So, in getting these invariants, in your example, there are some relations between them, right?
Between the variables?
Yeah. What? I mean, no relation? So is it always true that there's no relation?
No, in general there are no relations. No, you can always play with generators to have this. No. There is no any relations between those coefficients.
Prove that?
Well, I can't prove. I don't have a proof at all, but yes, I can prove.
Other questions? Thank you very much.
Thank you.